Alright, find dy dx in terms of y. Let's figure this one out here. So I haven't actually looked at this yet, so we're going to solve it together here. Here's my equation. Take the derivative. Derivative of tangent is secant squared times dy dx equals 1 plus dy dx. So here's my derivative. Now I got to get dy dx by itself. I'm going to subtract dy dx to the left. I think I'd like to keep secant positive. So I subtracted this to the left, and then I factored out dy dx. And now I'm going to divide. So dy dx equals 1 over secant squared of y minus 1. This is, I think, the solution. This is dy dx in terms of y. Now let's see what happens here. So part B, find the x and y coordinate of each point where the tangent line to the graph is vertical. So that's essentially where is the derivative undefined, right? So we're saying where is, for part B, where is secant squared of y minus 1 equal to 0? Vertical tangent line, we're thinking denominator is 0. So where is secant squared of y equal to 1? I would rewrite this as cosine squared, or 1 over cosine squared. And then we can just multiply by cosine squared. So really we're just finding when is cosine squared of y equal to 1. Square root of cosine squared is cosine, square root of 1 is 1. So where is cosine equal to 1? Or where is cosine equal to negative 1? Let's see. Cosine is 1 when y, on my interval, here's the interval. 2 pi less than x less than 2 pi. So that doesn't really come into effect now. But cosine is 1 every time we're at 0 or 2 pi. So it's like 0 plus 2 pi times n. Or it's pi plus 2 pi times n. So every pi around, our function will be 1. Those are just the y coordinates though. So we need to find an x coordinate. Tangent of y. Okay, so tangent of 0 and pi and 2 pi is always 0. So really we're saying tangent of y equals x plus y. Any of these y's that I'm going to plug in, tangent will always be 0. Tangent is sine over cosine, and at those locations, when cosine is 1 or negative 1, my sine value is 0. So this is 0 equals x plus y, or really x equals negative y. So all of the x and y coordinates we're trying to think about are the places where x equals negative y and we're between negative 2 pi and 2 pi. Let's see, so I've written way too large here and I haven't given myself enough space. So if that happens to you, just on your paper, just select it all and just move it. That'll work really well for you, right? Yeah, just maybe even shrink it a little bit. Really, I'm thinking it can't be 2 pi exactly, because that's not on my interval. And since it has those multiples of pi, then I think my only options are starting from the most negative to the most positive. It can't be negative 2 pi, so it has to be negative pi and pi. 0 and 0, because that's negative and positive, doesn't matter. And then pi and negative pi. If we test these in this example here, tangent of pi is 0, x and y cancel themselves out. If you tried to use like negative pi over 4, comma pi over 4, any other combo, tangent wouldn't actually be zero. So while we think there's an infinite number of solutions, the left side wouldn't actually work. So these are the only three. That's a pretty tricky question. Part C here, we're just taking another derivative based on what we got on this left side here. So dy dx equals 1 over secant squared of y minus 1. You can totally just use the quotient rule here, but also I do want to emphasize this this is a Pythagorean identity, secant squared of y minus 1, so you can rewrite this as 1 over tangent squared of y. I'm going to use the quotient rule on this one because I don't think a lot of us would recognize that immediately. So again, we don't need to simplify. Derivative of 1 is 0. I'm not going to write it because I took the derivative, so it's definitely not applying. Minus the top times derivative of the bottom. So derivative of secant squared of y, I'd have 2 times secant of y, so derivative of the outside, keep the inside the same, multiplied by derivative of the inside times dy dx. Derivative of negative 1 is 0, don't need to worry about that, all over secant squared of y minus 1 squared. The only other step we need to do is to plug in our dy dx. So really our last step is to just say, hey, our second derivative is negative 2 secant of y times 1 over secant squared of y minus 1. So get that all in terms of y instead of in terms of dy dx. That's what we did. And then keep the bottom the same. You don't need to simplify anything. You can if you want, but man, that's pretty nasty. So I don't know if I love this AP question. It seems like there's a lot of room for error and not much room for partial points, but it does have some good derivative concepts here. So good luck on this one. I know you can do it.